All right, so today we're gonna like really get down to the nitty-gritty, the basic building blocks of like pretty much everything around us, you know? We've
Absolutely.
got a whole stack of research here on molecules and condensed matter.
Yeah, it's gonna be a good one.
I'm excited about this one. It's gonna be interesting to see how we go from like, you know, individual atoms to like actual solids that we can like hold and touch and
Right, from the micro to the macro.
yeah, and what holds it all together and then like all the crazy properties that come out of, different arrangements and stuff. So,
Yeah, you've pulled together a really impressive set of sources here.
mm.
We've got everything from, how atoms link up in molecules to like the big picture of how they behave in solids and even some pretty wild quantum stuff.
I know, right? It's a lot.
We're going to break it all down, that distill into the key concepts without, drowning you in jargon.
That's the goal. That's the goal, right? So
Sounds like a plan.
let's jump right in.
Let's do it.
Molecular bonds. This is where it all starts, right? Like, how do atoms even stick together to form molecules in the first place?
Exactly. It's the foundation.
Yeah.
And the chapter really dives into covalent and ionic bonds as the major players.
Like the glue.
Yeah. And it all comes down to atoms wanting to achieve like the most stable electron configuration they can,
You want to be comfy.
exactly, comfy and stable. So let's start with covalent bonds. Imagine, atoms deciding to share their outermost electrons.
Okay.
This sharing creates a region of higher electron density right between the two nuclei, which are positively charged. And that concentrated negative charge is like an electrostatic glue holding them together.
Okay, so they're both positive, but then the negative in between, kind of?
Yeah, it's like a tug of war. They both want those electrons.
Right.
And the cool thing is these bonds, they often have a specific direction in space, which dictates, the overall three-dimensional shape of the molecule.
So it's not just random.
It's not at all. It's very organized. And a classic example of this is methane CH4, where carbon shares electrons with 4 hydrogen atoms in a very specific tetrahedral arrangement.
Oh, right. Methane. Yeah.
And don't forget the Pauli exclusion principle comes into play here too. Each shared electron region can only hold 2 electrons with opposite spins.
Right, right. So it's not just sharing, it's like organized sharing.
Exactly. Very organized share.
So then the way they share determines the shape, which I guess in turn affects how those molecules can then interact with other things, right?
Precisely. It's like
Yeah.
a domino effect.
Mm.
The shape influences their interactions.
Cool. Okay, so that's covalent bonds. What about ionic bonds?
So ionic bonds are kind of the opposite. Instead of sharing, you have one atom essentially giving 1 or more electrons to another atom.
Like a donation.
Exactly, a donation. And this creates atoms with a net electric charge. One becomes positive, the other negative, and then they're held together by pure electrostatic attraction.
Opposites attract.
That's it. A classic example is table salt, sodium chloride, NaCl, where sodium gives an electron to chlorine.
Oh, yeah, that's a good one.
It's like a complete transfer of wealth
Yeah.
in the electron world, and it leads to a very strong attraction.
Okay, so sharing versus transferring electrons. That's the basic difference, but then the chapter says it's not always black and white. Sometimes it's a bit of both.
You're right. It's more of a spectrum than a clear-cut either or.
And that's where polar molecules come in, right?
Precisely. So when the sharing of those electrons isn't perfectly equal, one atom might have a slightly stronger pull, you get a polar molecule.
One side's a little greedy.
Yeah, exactly. One end will have a slightly negative charge and the other end slightly positive, creating what we call an electric dipole moment.
Okay, I'm with you.
Water is a fantastic example of this, H2O. The oxygen atom pulls those shared electrons a bit closer than the hydrogens, giving it a slight negative charge, and the hydrogens slight positive charges.
And this is why water is so weird, right?
Well, weird in a good way.
Yeah, like all its superpowers and stuff.
It's this polarity that gives water a surprisingly high dielectric constant, which affects how it interacts with electric fields and why it's so good at dissolving so many substances.
So basically, water's slight greediness is what makes it so special.
It's a key part of its unique properties, for sure. And here's something really important to keep in mind. These same bond types, covalent, valent, ionic, and everything in between, they're the forces that hold atoms together in solids, too.
Wait, so like the same rules apply in a giant solid like a rock?
Pretty much, you can think of a solid as one giant molecule extending in 3 dimensions, linked by these same atomic interactions.
Wow, that's kind of blowing my mind.
It's all connected, and the chapter also touches on metallic bonds, which are unique to metals.
Yeah, I was wondering about those.
They involve a sea of electrons that aren't bound to any specific atom. They're free to move throughout the material.
It's like a giant electron party.
It is, and this electron sea is what holds those positively charged metal ions together.
So from these tiny connections, we build molecules, and then the same principles govern how they arrange themselves into solids.
That's the beauty of it. It's all interconnected.
Okay, that's amazing. Okay. Next up, the chapter talks about how molecules interact with light through molecular spectra.
Yeah, this is where we start to see molecules revealing their unique fingerprints, so to speak.
Like each one has its own signature.
Exactly. And unlike individual atoms, molecules can store energy not just in their electronic structure, but also in how they rotate and vibrate. And these energy levels are quantized,
Quantized meaning.
meaning they can only exist at specific discrete values. So when a molecule absorbs or emits light, it's essentially jumping between these energy levels.
It's like a staircase.
Exactly, and the specific frequencies of light involved that creates its unique spectrum like its own barcode.
Okay, so let's break it down, starting with rotation. The chapter mentions diatomic molecules as a rigid dumbbell. Why a dumbbell?
It's a helpful visualization. Think of a molecule with just two atoms connected by a fixed bond length, like two weights on a bar.
Yeah.
It simplifies things for analyzing their rotation.
Excellent.
And quantum mechanics tells us that the energy of those rotations isn't continuous. It comes in specific packets defined by this formula. E sub L equals L times L plus 1 times h bar squared divided by 2.
Okay, it sounds
It
complicated.
looks scary, but it's really not so bad.
Yeah.
L is just the rotational quantum number, which can be 0, 1, 2, and so on. And I is the moment of inertia.
Moment of inertia.
Now, think of it as a measure of how resistant an object is to changes in its rotation. For our dumbbell molecule, it depends on the masses of the two atoms and the distance between them.
So a heavier molecule or a longer bond will have a bigger moment of inertia.
Exactly, and that means different rotational energy levels.
Okay, I think I'm following. So each molecule has its own set of allowed rotational energies, but how do they transition between those levels?
They follow a rule called the selection rule, which says delta L equals plus or minus 1.
Delta L.
Yeah, it just means the change in LL. So when a molecule absorbs or emits a photon, a little packet of light energy, its rotational quantum number can only change by one step up or down.
Like it can only move one rung up or down on the ladder.
A perfect analogy. This leads to a series of specific frequencies of light that each molecule can interact with.
So it's like shining a light and seeing which colors get absorbed.
And that pattern, those frequencies, act like a fingerprint, telling us about the molecule's rotation.
Wow, so we can actually figure out a molecule's shape and mass distribution just by shining light on it.
Pretty cool, right?
That's super cool. Okay, so we've got the rotation part down. What about vibrations?
So in addition to rotating, molecules are also constantly vibrating. Think of those atoms as being connected by tiny springs.
Okay, I can picture that.
The energy of those vibrations is also quantized. It's not just any random energy, and we can model it using the simple harmonic oscillator, just like a mass on a spring.
I vaguely remember that from physics class.
The energy levels are given by E sub n equals n plus 1/2 times h bar times omega, where n is the vibrational quantum number 0, 1, 2, and so on, and omega is the angular frequency of the vibration.
Okay, starting to lose you a little bit with the Greek letters.
Don't worry about the specifics too much. Just know that this frequency omega depends on how stiff the bond is between the atoms and their reduced mass.
Reduced mass like a discount on mass.
Kind of. It accounts for the fact that in a two-atom system, both atoms are moving relative to their common center of mass.
Right, it's like a dance. They're both moving around.
Exactly, a delicate dance. And the cool thing about these vibrational energy levels is that the spacing between them is constant delta, E equals h bar omega.
Constant spacing, so like evenly spaced rungs on a ladder.
You got it.
Okay, I'm with you, but real molecules aren't just doing one or the other. They're rotating and vibrating at the same time, right?
Absolutely. They're multitasking pros, and the chapter combines these two types of motion, giving us the total energy E sub NL equals L times plus 1 times h bar squared over 2, I plus n plus 1/2 times h bar times the square root of k prime over m sub r.
Okay, you lost me again.
Don't worry too much about the formula. Just remember, it combines both motions.
Got it. And the selection rules for transitions between these combined levels are also combined, right?
You're sharp. You remember that, so delta L equals plus or minus 1 and delta N equals plus or minus 1.
So it can jump up or down one step in both rotation and vibration at the same time.
Precisely. And this combination leads to what we see as band spectra.
Band spectra, because
Each vibrational transition, a change in N, can be accompanied by several different rotational transitions. Changes in L of ion.
so instead of sharp lines in the spectrum, we see bands.
Exactly. Bands of closely spaced lines. Each band corresponds to a specific vibrational transition, and the individual lines within that band correspond to the rotational transitions.
So it's like each rung on the vibrational ladder has its own set of closely spaced rotational sublevels.
Another great analogy.
Cool. So by analyzing these band spectra, we get a super detailed picture of the molecule.
Absolutely. We can identify the types of bonds, present their strengths, even the structure of the molecule. Different bonds vibrate at characteristic frequencies, giving us a unique spectral fingerprint.
It's like molecular detective work.
Exactly, using light to decipher the secrets of molecules.
Okay, I love that. So we've gone from bonds to rotations and vibrations. Now the chapter switches gears to talk about solids, right?
Yep. From dynamic molecules to the more static arrangement of atoms in solids, the condensed phase.
Where things get a bit more rigid.
In a sense. And the first distinction the chapter makes is between crystalline and amorphous solids.
Crystal, I get like a diamond, but amorphous, is that like Play-Doh?
Not quite. Play-Doh is more of a complex mixture, but think of glass or butter for amorphous solids.
Okay, so what's the fundamental difference?
It all boils down to long-range order. Crystalline solids their atoms are arranged in a very regular, repeating three-dimensional pattern that extends throughout the entire material like a perfectly tiled floor.
Okay, I see.
Amorphous solids, on the other hand, only have short-range order. Their atoms might have some local organization, but this order doesn't extend over long distances. It's more like a snapshot of a liquid where the atoms haven't had time to settle into a perfect arrangement.
So one's all neat and tidy and the other's a bit more random.
You got it. And this difference in order leads to some very different properties between the two types of solids.
Interesting. Okay, so then the chapter dives deeper into crystalline solids, talking about the crystal lattice and basis. Can you unpack those?
Sure. Imagine an infinite, perfectly repeating array of points in three-dimensional space. That's your crystal lattice. It's like a scaffold.
Okay, a framework.
Exactly. And now at each of those lattice points, we place an identical atom or group of atoms. It's called the basis.
So the lattice is the pattern and the basis is what gets repeated.
Bingo. The crystal structure is then created by repeating this basis at every single point on that lattice. So the lattice defines the geometry, and the basis is the repeating motif.
Makes sense. So like a wallpaper pattern.
Perfect analogy. The lattice is the grid, and the basis is the design element.
Okay, that makes it much clearer. And the chapter lists some common types of crystal lattices, like simple cubic, face-centered cubic, body-centered cubic, and hexagonal close-packed.
Right, those are just different ways to arrange those lattice points in space, leading to different overall symmetries and packing efficiencies in the resulting crystals.
So some are more tightly packed than others.
Precisely. And that affects their properties like density and how they respond to stress.
Okay, cool. And then the chapter brings back those bonding types we talked about earlier, but now in the context of solids.
It all comes full circle. So we have ionic crystals like table salt, again, sodium chloride, where the lattice points are occupied by positively and negatively charged ions held together by electrostatic forces.
Still sticking together.
Always. Then we have covalent crystals like diamond and silicon, where the atoms are linked by those strong directional covalent bonds, forming a continuous network throughout the crystal.
Super strong bonds.
Very strong. And finally, we have metallic crystals, where those metallic bonds with their sea of delocalized electrons hold the positively charged metal ions in the lattice.
So it's like the electrons are the glue for the whole structure.
Exactly. And the non-directional nature of those metallic bonds often leads to very efficient packing of atoms. That's why many metals adopt those close-packed structures like face-centered cubic and hexagonal close-pack.
So they can squeeze in more atoms.
Exactly, maximizing their density.
And then there's this little bit at the end about crystal defects.
Right, so even those seemingly perfect crystal structures, they're not actually flawless real crystals, always have imperfections.
Nobody's perfect.
Exactly. And these defects can have a surprisingly big impact on the material's properties, how strong it is, how it conducts electricity, even its optical properties.
So flaws can actually be important.
In a way, yes. So we have point defects, which are localized imperfections, like vacancies, where an atom is missing interstitial atoms, where an extra atom is squeezed in, and substitutional impurities, where a foreign atom replaces one of the original atoms.
So it's like a little bit of chaos in the perfect order?
Exactly. A little bit of spice. And then there are extended defects like dislocations, which are basically line defects that disrupt the regular arrangement of atoms over a larger scale.
So not just a single atom out of place, but a whole line of them.
Exactly. And these dislocations can actually make a material stronger by making it harder for those planes of atoms to slip past each other.
Huh. That's counterintuitive.
It is. Materials science is full of surprises.
Okay, I'm starting to see why this is such a rich field of study. Okay. Moving on, now we're getting into energy bands and solids. This is where things start to get really interesting in terms of electrical behavior.
Absolutely. This is where quantum mechanics really takes center stage. So when you bring a huge number of atoms together to form a solid, their individual atomic energy levels, which are normally discrete, they start to interact and broaden into continuous bands of allowed energies.
It's like those energy levels get smeared out.
Exactly. It's a consequence of the atoms being so close together and the Pauli exclusion principle, which says no two electrons can occupy the same quantum state.
So no overcrowding in those energy levels.
Precisely. And we call the highest energy band that's filled with electrons at absolute zero the valence band, because it contains those valence electrons, the outermost electrons of the atoms.
Okay. And above that is the conduction band.
Exactly. And the conduction band can be empty or partially filled. But the crucial factor that determines whether a material is an insulator conductor or semiconductor is the size of the energy gap between these two bands.
The energy gap.
Yeah, it's also called the band gap. It's a range of energies where no electron states are allowed. It's like a forbidden zone.
Okay, so a large energy gap means it's hard for electrons to jump from the valence band to the conduction band.
Exactly. And that's what makes a material an insulator. It takes a lot of energy for electrons to overcome that barrier and become mobile charge carriers in the conduction band.
So they're stuck in the valence band.
Pretty much. Whereas conductors, they have either a partially filled conduction band or the valence and conduction bands overlap.
So there are already plenty of electrons free to roam around.
Exactly. And they can easily move and conduct electricity. And then we have semiconductors, which fall somewhere in between.
The Goldilocks of materials.
I like that they have a relatively small energy gap, typically around 1 electron volt. So at room temperature, some electrons can gain enough thermal energy to hop across that gap into the conduction band, allowing for some electrical conductivity.
But not as much as a metal.
Right. And what's really cool about semiconductors is that their conductivity can be dramatically increased by either raising the temperature or by introducing impurities, which we'll talk about more later.
So we can actually control their conductivity.
Exactly. That's what makes them so versatile. And the chapter also mentions a couple of interesting phenomena related to energy bands, dielectric breakdown, and photoconductivity.
Yeah, what are those all about?
So dielectric breakdown happens in insulators when you apply a really strong electric field. It's like pushing those electrons way too hard.
Like forcing them across the gap.
Exactly. That intense field can give those electrons in the valence band enough energy to suddenly jump across the gap into the conduction band.
And that's bad, right?
It can be. It often leads to a sudden surge of current, which can be destructive.
Okay, got it. What about photoconductivity?
Photoconductivity is more of a gentle process. It happens in semiconductors when they absorb photons, particles of light that have energy greater than the band gap.
So light can also push electrons across the gap.
Precisely. It excites those electrons from the valence band up into the conduction band, creating more free charge carriers and increasing the material's conductivity, but only while the light is shining.
So it's like a light switch for conductivity.
Exactly. Light can temporarily make the semiconductor more conductive.
That's pretty wild. Okay, now let's talk about the free electron model of metals. It sounds kind of oversimplified, treating electrons as if they're just bouncing around freely.
It is a simplification for sure, but it's surprisingly effective at explaining many of the electrical and thermal properties of metals.
Okay, so how does it work?
Basically, we ignore the detailed interactions between the valence electrons and those positively charged ions, except for the fact that the ions create an average potential that keeps the electrons confined within the material.
So we're just focusing on the electrons?
Yeah, we treat them like a gas of free particles moving within the metal.
Oh.
But even these free electrons, they still have quantized energy levels because they're confined within that three-dimensional space of the metal.
Right. They can't just fly off into space.
Exactly. And we can model the metal as a box. And the energy levels are given by this formula, E sub nx n I n's equals nx squared plus na squared plus na squared times pi squared times h bar squared divided by 2 ml squared.
Okay, I'm not even going to try to decipher that.
Don't worry about it. The main point is that even though they're free within the metal, they still have quantized energy levels.
Got it. And then the chapter introduces the density of states. What's that all about?
The density of states, denoted by G of E, tells us how many available energy levels there are per unit energy range at a particular energy E.
So like how many parking spots are available at each energy level?
I like that analogy. And for the free electron model, the density of states is proportional to the square root of the energy.
So more parking spots at higher energy levels.
Exactly. And then we have to figure out how these available states are actually filled by the electrons. And that's where the Fermi-Dirac distribution comes in.
Another scary name.
It sounds intimidating, but it's a crucial concept. It's a function of E that gives us the probability that an electron state with energy E will be occupied by an electron at a given temperature.
So it tells us how the electrons are distributed among those energy levels.
Precisely. And it's important because electrons are fermions, meaning they obey the Pauli exclusion principle. No two electrons can be in the same state.
Right, no overcrowding.
And at absolute zero, the Fermi direct distribution is like a step function. All energy levels up to a certain energy called the Fermi energy are completely filled, and all levels above it are completely empty.
Okay, so the Fermi energy is like the highest occupied energy level at absolute zero.
Precisely. It's like the sea level of the electron sea, and the Fermi energy is a fundamental property of a metal. It depends on the concentration of those free electrons.
So more electrons means a higher Fermi energy.
Exactly. And the free electron model also lets us calculate the average energy of those electrons at absolute zero, which is 3/5 of the Fermi energy, and even define a Fermi speed, which is the speed of an electron with kinetic energy equal to the Fermi energy.
And that speed is...
Really, really fast, much faster than the average speed of those electrons.
Okay, so we've got this simplified model that tells us a lot about how electrons behave in metals. But now let's go back to semiconductors. They seem to be the real stars of the show.
They are pretty amazing.
Yeah.
So now that we understand energy bands, we can really dive into the unique properties of semiconductors. Remember, they have that small energy gap that makes them so special.
Right, the Goldilocks gap.
Exactly.
Okay.
So in a perfectly pure or intrinsic semiconductor like silicon or germanium at temperatures above absolute zero, some electrons will gain enough thermal energy to jump across that gap from the valence band to the conduction band.
They can make the leap.
They can. And for every electron that jumps it, leaves behind an empty state in the valence band, which we call a hole.
A hole like a missing electron.
Exactly. And here's the thing. Those holes can actually contribute to electrical conductivity, too. They act like positively charged particles.
Wait, what? How can an absence of something act like a particle?
It's a bit mind-bending, but think of it this way. An electron in a nearby part of the valence band can move into that hole, effectively making the hole move to where the electron was.
So it's like a game of musical chairs.
Kind of. The holes are moving around just like the electrons.
Okay. I can sort of picture that. So in an intrinsic semiconductor, we have equal numbers of electrons in the conduction band and holes in the valence band, and they both contribute to conductivity.
Precisely. But this conductivity is still much lower than a metal because the number of these thermally excited charge carriers is relatively small.
But we can change that, right, by doping.
You got it. Doping is like adding a pinch of spice to our semiconductor recipe. It's the intentional introduction of a small, precisely controlled amount of impurity atoms into the crystal lattice to change its conductivity in a big way.
Okay, so it's not just about purity, it's about controlled impurity.
Exactly. We can fine-tune the properties by adding just the right amount of the right impurities.
So how does it work?
There are two main types of doping. We can add donor impurities like phosphorus or arsenic into silicon, creating what we call an N-type semiconductor. N for negative, because we're adding extra electrons. These donor atoms have one more valence electron than silicon. So when they replace a silicon atom in the lattice, that extra electron is only weakly bound and can be easily excited into the conduction band.
So we're boosting the number of free electrons?
Precisely increasing the conductivity. And on the flip side, we can add acceptor impurities like boron or gallium into silicon, creating a P-type semiconductor.
P for
positive, because we're essentially creating more holes. These acceptor atoms have one fewer valence electron than silicon. So when they replace a silicon atom, they create a missing electron or a hole in the valence band.
So we're boosting the number of holes, which are like positive charge carriers.
Exactly. And both types of doping change the conductivity dramatically. And the chapter also mentions that doping shifts the Fermi energy within the semiconductor.
Right. The Fermi energy was that sea level of the electron sea?
Exactly. So in an N-type semiconductor where we've added more electrons to the conduction band, the Fermi energy shifts closer to the conduction band.
Like the sea level is rising.
And in a P-type semiconductor where we've effectively increased the number of holes at the top of the valence band, the Fermi energy shifts closer to the valence band.
So the sea level is dropping.
Exactly. And the extent of this shift depends on the type and concentration of those dopant atoms.
So it's all about fine-tuning.
It is. And this ability to precisely control the type and concentration of charge carriers through doping is what makes semiconductors the foundation of modern electronics.
It's like we're playing with the fundamental building blocks of electricity.
We are. And that leads us to the section on semiconductor devices, which explores the magic of PN junctions.
Okay, PN junctions remind me of diodes.
You're right. A diode is basically a p-n junction. It's formed when you bring a p-type and an n-type semiconductor material into close contact.
So what happens at that interface?
Some interesting stuff.
Yeah.
Basically, you have this huge concentration gradient of electrons and holes at the junction. The electrons from the n-type side want to diffuse over to the p-type side where there are lots of holes and vice versa.
They're trying to balance things out.
Exactly. But as those electrons and holes diffuse, they leave behind immobile charged ions near the junction, positively charged donor ions on the n side, and negatively charged acceptor ions on the p side.
So it's like a separation of charges.
Exactly. And this region near the junction where those mobile charge carriers have been depleted is called the depletion region or the space charge region.
Okay, and this separation of charges creates an electric field, right?
You got a built-in electric field across the junction pointing from the n side to the p side.
Okay, and this electric field affects how current can flow across the junction.
Precisely, the chapter introduces the ideal diode equation. I equals I sub s times the quantity e to the v over kt minus 1, which describes the relationship between the current I flowing through the junction and the voltage V applied across it.
Okay, lots of symbols there.
Don't get bogged down in the details, just know that this equation tells us that the current flow is very sensitive to the applied voltage and the direction of that voltage.
Okay, so what happens when we actually apply an external voltage across this PN junction?
If we apply a forward bias, meaning we connect the positive terminal of a battery to the p-type side and the negative terminal to the n-type side, we're essentially opposing that built-in electric field.
We're pushing against it.
It's exactly. This reduces the width of that depletion region and lowers the energy barrier for those majority charge carriers to flow across the junction.
So current can flow easily.
Exactly. But if we reverse the polarity, apply a reverse bias, the applied voltage actually reinforces the built-in electric field.
So it's like we're making the barrier even higher?
Precisely. And that makes it very difficult for the majority charge carriers to flow across, resulting in only a very small current called the reverse saturation current.
So current can flow in one direction, but not the other.
Exactly. That's the defining characteristic of a diode. It's like a one-way valve for current.
Very cool. And then the chapter mentions transistors and integrated circuits. They're basically built from these PN junctions, right?
Exactly. Transistors are semiconductor devices with more than one PN junction. They're the workhorses of modern electronics.
So they're like diodes on steroids?
Kind of. There are bipolar junction transistors, BJTs, which have 3 semiconductor regions, and field effect transistors, FETs, which use an electric field to control current flow. And both types of transistors can act as amplifiers or switches, controlling the flow of much larger currents using much smaller control signals.
And then integrated circuits are basically millions or billions of these transistors all crammed onto a tiny chip.
That's right. It's mind-boggling when you think about it. All the complexity of our smartphones and computers comes down to the precise arrangement of these microscopic PN junctions.
It's like building a city from individual bricks.
And the incredible thing is we're still finding new ways to miniaturize and integrate these components, pushing the limits of what's possible.
It's amazing to think about. Okay, so to wrap things up, the chapter ends with superconductivity, which sounds pretty futuristic.
It's a fascinating phenomenon that happens in certain materials when they're cooled below a specific critical temperature in the superconducting state. They exhibit exactly 0 electrical resistance.
Zero resistance, so like a perpetual motion machine for electricity.
It's not quite perpetual motion. There's still some limitations, but it's pretty close. Once a current is established in a superconducting loop, it can flow forever without any energy loss.
That's mind-blowing. How does that even work?
The chapter touches on the Berdeen-Cooper-Schrieffer BCS theory, which explains it in terms of quantum mechanics. It proposes that at very low temperatures, there's an attractive interaction between pairs of conduction electrons mediated by the vibrations of the positive ions in the crystal lattice.
So the lattice is actually helping the electrons pair up.
In a way, yes. These pairs of electrons are called Cooper pairs, and this weak attraction overcomes the usual repulsion between electrons. And below the critical temperature, these Cooper pairs condense into a macroscopic quantum state where they all behave collectively.
So they're all moving in sync.
Precisely. And this synchronized movement allows them to glide through the crystal lattice without scattering off the ions, which is what causes resistance in normal materials.
So no scattering, no resistance.
Exactly. It's a truly remarkable quantum phenomenon.
And potentially revolutionary if we can figure out how to achieve it at higher temperatures.
Absolutely. The search for high-temperature superconductors is a very active area of research. And who knows what amazing technologies might emerge if we can harness this phenomenon more effectively.
Well, this has been a whirlwind tour of molecules and condensed matter, from the tiniest bonds to the weirdest quantum effects.
We've covered a lot of ground, but hopefully we've given you a solid understanding of how the microscopic world influences the macroscopic properties of materials, all the way from individual molecules to those incredible solids.
Yeah, I feel like my brain is definitely a bit more condensed now.
Condensed in a good way. I hope we've covered all the major points from your chapter on molecules and condensed matter, giving you a comprehensive overview of this fascinating field.
Definitely lots to think about. Thanks for guiding us through it.
My pleasure. It's always fun to explore the wonders of the molecular world.
Absolutely. All right, until next time, happy diving, everyone.
See you next time.
Bye.